Thank you for inviting me. Right, then I'll just start. So first of all, hello to all. My name is Xia Chen. I am a PhD candidate in Leibniz University of Hanover, Germany. And my supervisor is Professor Philip Geyer, the chair of the Sustainable Building System Group in Hanover. It is a great honor to be invited in here. Thank you for the invitation and share our research work. Today, I would like to introduce the causal inference in the building engineering domain, and more specifically would put it into the context of the energy efficient building design process. Why is it necessary and how it would shape the landscape of our domain research. So this study is actually one of the components of our general research scope, a machine assistance to support the decision-making process and achieve a general higher intelligence in sustainable engineering design. And this objective is actually composed in threefold. So firstly, we try to develop a machine assistance framework that can accept different methodologies to conduct this multidisciplinary evaluation regarding the energy performance, LCA, cost, and etc. And importantly, also can accept incomplete input to conduct uncertainties analysis, because it's kind of like a big deal in the design stage because the information is limited. And based on that, we also try to integrate the domain knowledge-based method, because we realize that if you just use the data-driven method in our domain, which has a lot of principles, rules, regulations, it will be less efficient. So we also try to embed it with the logisticism representation of the domain principles. And finally, we try to enable our machine assistance framework to conduct reasoning and also answer what-if questions. So actually, these three folds adds up together, become the purpose of the paper we present today. We try to embed logisticism representations into the machine assistance to conduct reasoning analysis and answer what-if questions in the engineering design. And today, of course, we focus on this top component, causal inference. I'll start with two simple points: the what-if questions in the design process, and what can we extract from this process. This is the Empire State Building, one of the most famous buildings globally. And the fact is, before the final blueprint is approved, it had gone through up to 50 different versions. And here we can see 4 of them, these different versions. And apparently, the designer must go through a lot of assumption scenarios. And that leads to the question of what if. They are intuitively generated and commonly asked during the design process. And engineer and architects need to inherently conduct design decisions, progressing from one phase to another. So they either use the domain knowledge, simulations, or data-driven method to acquire this sequential feedback. And how to properly give informative feedback to this kind of question becomes the core of solving this decision-making problem during a design process. To figure this out, we firstly take a closer look of the design process itself. We summarize and describe them in different paradigms in our paper. In the first paradigms, I personally call it the dark age, without any external resources or assistance. The architects only can use its personal ability to design. So they have an idea, they designed it. Because it lacks of feedback, so the performance is hard to guarantee, and it's heavily relies on its personal ability scope. And then it's the second paradigms. We have computers. We have computers with simulations and surrogate models to run them repetitively with combinations. And the user can receive feedbacks for design optimization. So it saves a certain amount of time because this simulation can bring quite accurate results and guarantee the performance. And we kind of categorize the most of current decision support systems in this class. However, running and building simulations are usually time-consuming. And this is the point we try to take a further step. If we review the way how human designers think, we realize that in here, what we call idea is actually made of two parts. One part, it's more fundamental. We call it knowledge. It barely changed. It's reusable. It's stackable. It contains high density information for our every design. We have to use it. For example, like some basic physical principles, the directions of causality, and etc. They are normally present as a formula, or we can call it a symbolism representations. And another part, it's more implicit. We call it experience. It's more related to personal preference or your individual cases, design cases. And it's more similar to the connectionism because it's more like your intuitions. You want to do, or you want to design your building this way because it's from your taste or from another individual cases reasons. So based on that, we propose to use a separate tool to deal with the knowledge and experience individually. So the knowledge can be inherent from external resource, or it can be discovered from data. So we don't have to redo this fundamental knowledge in simulation again and again. And it will enable designer to focus on the intuitive exploration based on its personal preference in the higher efficiency behavior. In this study, we kind of emphasize this inheriting knowledge as the causal inference logic. So what is the causal inference logic, and what's the necessity of it? This topic is initiated from the medical statistic research, and up to now already have quite a lot of solid studies. And we found this topic is also really important to our domain. Here we make two examples to demonstrate this concept. Let's start from this left side. Say we have a data set for machine learning model to figure out what should we do to enhance the building energy efficiency. And we know that the building area would both affect, or it is the common cause of the building structure strength and energy efficiency. If this building is small, so it's more compact, so it has more higher energy efficiency, but it doesn't need a really high structure strength. But if a building is big, then it's normally have a higher structure strength and less energy efficiency, generally speaking. So if we don't control this building area variables in the data, or we just don't carefully review its distribution, the machine learning model would get the wrong conclusion because the variables, these two are correlated, and it might suggest you that you have to adjust the building structure strength to change the energy efficiency. And another situation is, say we want to optimize the building occupancy, and because it's list variables and the building area are the causes for the building operational cost. And if we have a data set with a fixed cost variables, if we don't know that, the occupancy will also correlate it to the building area and might lead to another wrong conclusions. And these two scenarios, we call it confounder and the correlator situations in the causal model. And of course, these two examples can be easily identified using our common sense. But if we put this concept in a broader and more complex design situation with more parameters, we might find it hard to have the confidence to say, okay, we can avoid all these pitfalls.
Sorry to interrupt. Yes. I have a question. So
yes,
yeah, this is I mean, great diagram. Did you ever have any data set that shows the correlation between the building structure strength and the building energy efficiency without controlling the building area?
Actually, we have a case study like in my later presentations that will show. But if you specifically refer the strengths and efficiency, no, we don't have the data set. It's more like I demonstrate a concept of that.
I see. Or did you analyze maybe some other like in the second diagram? Is there any correlation between the building area and the building occupancy if you control the building operation cost?
So if you it's kind of like the mind game. You have a fixed building operation cost, and you have a really small building, and another one is a really large building. And if they have the same operational cost, so the large building would tend to have less occupancy in average and bigger area. So this situation, so it would be if we have a data set, have a different buildings, and they have the same building operational cost if we sample it really pool, and the machine learning have the inputs like the building area, so it will find these two would have negative correlations with each other, so it would get the wrong conclusion.
Thank you. So it's still in the concept yet, right?
Yes, but later in the case study, I will elaborate in the case in the data. Right. So where we are. Okay. Today, we say if we don't carefully review this data, it would lead to some pitfalls. And today, adapting machine learning and artificial intelligence methods into our domain, it's getting popular. And the risk of making such mistakes is actually rising because we tend to forget or less carefully check the condition that machine learning model normally or usually assume that the input parameters are independent or even independent and identically distributed, which is IID situation. So it means the probability distribution of each parameters or features should have no dependence on other features. However, the design process itself, it's a series of sequential interactions with dynamic conditions. So if we don't carefully review the data, it might contain potential confounding bias in the data set. And most of machine learning model is taking this IID condition as a precondition, but in our domain, this condition is really underappreciated. And such examples can be easily found not only in the design process, but also in the general building engineering domain. Say we want to dimensioning a building energy system, and there are some features, and we can easily find some causation between the indoor temperature, outdoor temperature, building occupancy, such examples. Right. So to address this issue, of course, we have quite a lot of semantic rule-based methods or expert systems comes to help. We call it first-order method for causal encoding. However, they have the limitations to exhaust the extent to different design schemes because they normally requires manually pre-definition and hard coding. So this is where the causal model comes to the rescue. It has the mathematical rigor approach to find and encode causality directly from data with no specific semantic grounding required. Because of that, it can be extended easily in the digitalization process, and the outcome can be accumulated and reused in different cases. We call it the second order method for causal emergence, the ability to learn causality directly from data. And in general, this causal model have two research objectives. One is identifying causal relationships, and another one is quantifying causal effects. And these two are really big topics, contains really comprehensive theories and different algorithms. I think we don't have time to expand them in detail and elaborate every piece of information in here, but I will give a nutshell description. They both use the probability asymmetry of independence in causality to identify and quantify them, which means changes in the probability of the cause and changes in the probability of the effect condition on cause are independent. And this situation, if you reverse it, it won't stand. And for the causal relationships, the community normally use the graphical representation, direct acyclic graph, also DAG, to represent it and come with theorems to have a flexibility to test the features dependencies and to accept hidden variables. And for causal effects, the community normally use the structure causal models SCM and potential outcome framework to analyze it. And we realize that these two objectives align perfectly to what we mentioned before, the knowledge and experience. The causal structure finding is more related to the knowledge itself. Methods such as these separations allows us to check input independence in a mathematical way. It stores information of causal dependence, and list dependence are less likely changed, and it can be reusable. So it's kind of like knowledge. And for the causal effect, it more depends on the design case. Once we fix the causal skeleton, we can manipulate the variables without the risk of getting biased results. We normally use this average treatment effect or conditional average treatment effect to quantify that. These two are the methods. I think it's from the potential outcome framework.
Xiaoqian,
And this, yes, please.
I imagine that the causal skeleton may change by building to building, given that the relationship between the equipment, people behavior, the type of behavior that people can do. So would you need to recreate it every time? Or do you have a technique where you have a generalizable skeleton and then it can be automatically adapted to the building? But how can that be done during the design phase?
Right, that's a really nice question. So the causal skeleton is actually store the information of this causality, like you have the floor heights, you have the building area, and this would affect the building volume. So this kind of dependence, it's kind of unchanged from buildings to buildings. But if with the ongoing design stage, with more details, of course, you would have different details dependence with each other. So of course, our objective is to go for the universal adaptable causal graphs. But so far, we would say that in the fundamental part, it can be reusable. But if you go into really details, you might have to use these separations to generate it from the data. Yeah, so partially it can be reused and partially it can't. It depends on the level of details. So I don't know if that answers the question. And later I would have a case study example to demonstrate this, all this stuff. So don't worry. Right, and then I will continue. So right, I was saying this knowledge and experience and link it to the research objective of causal relationships and causal effects. And this transition is an important step of encoding knowledge into data-driven process. And we want to raise this approach and adapt it into the new paradigms we mentioned before, the knowledge encoding tool. So yeah, that's on this slide. So here is the 4 steps of causal inference framework we propose in the building design process. In the first part, we use causal finding algorithm to discover the causal relationships from the data. And then we can use our domain knowledge to test it and trim it. This part would determine the skeleton of causal relationships amongst features. And in the second part, we need to firstly identify the desired treatment and outcome, our targets, and then formalize the causal effect of potential outcome given the set condition from the skeleton. And the advantage to adapt this framework in the building design process is the causal skeleton draws a really clear boundary for a certain building design stage that all the variants or design alternatives follows the same intellectual context. And the causal model grows with the design stage detailing and allows for incomplete inputs for inference of answering what-if questions. And it could become a really handy machine assistance. Right. So we can take a fresh look of the design assistants. We categorize them by dimensions. In one-dimensional scenario, we use simulations to answer what-if questions. But each run of these simulations can only reveal one point of design scenario, and we have to run it many times manually to proceed from one phase to another. And in the second dimensional scenario, we combine with the heuristic algorithm to accelerate this potential design space exploration process in a more efficient behavior. It can generate a Pareto front, which gives the optimized scenario set. And we can explore scenarios from one phase to next possible potential phases. And in the three-dimensional scenario, we combine with the causal model, which encoded the causality relationships knowledge. So we can also check the design variants or alternatives in the current and the previous design stages, which we call it invertible assumptions, and explore the alternatives potential design space accordingly. And that is, in this context, we call it what if I had done questions. So these combinations would inherit the fast and flexible characteristic of the data-driven approach while benefit from the causal sequential logic from the knowledge-based extraction. That is the design assistance dimension. Right, and start from this slide, I would further elaborate and demonstrate the causal model in a case study. And one of the advantage in adopting causal model research in our domain is we have many well-developed, sophisticated first principles models and simulations, which already encodes this rules-based knowledge through efforts by engineers and experts. And it could provide a really solid foundation for our causal research and for the counterfactual validation. And in this case study, we would illustrate how the causal inference logic extract from the simulation data and how it will benefit the decision-making support. This data set is it's from our previous research, which contains 1,000 simulations in various scenarios. We use the NH+ to generate the data in the climate zone of Munich, Germany. And here shows the different shape, kind of like illustration of different shapes of different building scenarios in this 1,000 simulations, and parameters and their sampling ranges. And we choose this data set for the case study based on two major reasons. So the first is this data set emphasizes the building in different geometric properties. It serves for building performance evaluation in the early design phase, which contains relatively simple building parametrics representations with really comprehensive causal relationships that could be examined by our common sense. And the first principle simulation process itself ensure that there's no hidden variables or another factors to affect this result, and it will provide a nice verification for extracted knowledge. And the second reason for this data set is in our formal research, we test its accuracy through a real-world case, which means that it's solid for validating the causal effect estimation. Based on the generated data set, we apply the causal structure finding algorithm to extract a causal relationship from data. As you can see, the data set can be generated via modeling or directly collected from the real world. Such data set already embedded with the causal inference logic. And the structure finding algorithm can extract such relationships in a mathematical way without semantic context required. In here, we use a common algorithm in the structure finding community, which calls greedy equivalent search. It's also heuristic. algorithm, and store and extract this information and store in the graph. And here is the outcome, the graph. We use a tool, it called, to demonstrate it, it called deficiencies. And this deficiencies is developed by the Johanna's Extor teams. It gives a really nice illustration of this causal skeleton. Each of this box would represent a feature, and these arrows represent the cause effect relationship. And in this graph, you can see that some of these arrows are more thick. It means the direct effect. This direct effect means if we remove one of these from the diagrams, it would have no longer be any causal effect between the corresponding variables. So that it's how we read this graph. And as we can see that the result is quite accurate. The causal relationships also reflect a certain level of kinships in design process. Normally, we will fix the geometry first, the ground floor area, number of floors, heights firstly, and then we try to determine the wall-to-window ratios. And then we go for windows, we go for systems, we go to material property and so on. And it's worth mentioning that in the original relationship output, the only relationship we need to trim it based on our domain knowledge is the bidirectional errors between the window area and the external wall area. This means that the algorithm fails to conduct the cause-effect direction between these two features from a given data. Yeah, because as you can see, there's a lot of confounders in here, so it's quite normal. And in fact, the need for removing the bidirectional error perfectly presents the example of correlation does not imply causation in the building design domain. And this process provides a really good channel or nexus for integrating our domain knowledge with the data-driven method, providing a certain level of interpretability and testability against the domain experience within the design space. And because once we fix this skeleton, it will greatly determine how we quantify the causal effect. Yes, I see there's a...
Yes, I think Sapno has a question.
Yeah, I have a couple of questions.
Yes.
The first one is related to, can you confirm that this diagram was automatically created by the GT? Is that the objective?
This diagram is actually the relationships is found by this algorithm, and deficiencies is kind of the canvas, you know, to present it.
Okay.
Yeah.
Which is the benefit of having this relationship already kind of automatically determined, given that we already have a good physical understanding of those, and usually the unknown part are maybe the coefficients that we input or some other parameter that we may not be sure about how to model, for example, occupant behavior. On the opposite, the effect of windows area or the U value of the windows on the heating loads is kind of clear. And some other aspect, like for example here, there is not a differentiation between the different orientation when we know that the importance of the, for example, the solar heat gain coefficient will depend on the orientation. It's very important on the south side. It may not be important in the north side. So I'm wondering why you choose this direction of modeling.
Right. I'm not sure if I understand this the questions correctly. You mean that can you elaborate again?
Let me rephrase it. You said that this diagram was automatically extracted and created by the GES algorithm and then visualized by the GT. And I'm wondering, why is this beneficial, given that we know quite well the relationship of how, for example, the windows affect the heating load, or how the U value of a windows affect the heating load. But there are other causal relationships that we are not very good at understanding or modeling, like how people behave, which are their preferences. And so why focusing as a first step on the physical domain, where we already know quite a lot, and not on the people domain, where we have a relatively limited knowledge of how to model that?
I understand. Okay. Thank you, Professor. This is a good question. So our objective of the paper title is introducing the causal inference in our domain. And to be honest, the causal inference, this subject or this subject is quite large. So in this paper, we kind of like the proof of concept in here. Of course, I understand that there is a lot of causal investigations or unsolved problems in the building engineering domain. But the reason we choose this data set and demonstrate is to prove that this algorithms or this whole process is solid and it's correct based on our judge or our common sense. So if that's the stance, we will have more attentions in the domain researcher that can involve to this topic and actually explore into the questions you mentioned into more sophisticated situation. I don't know if that answers the question.
Thank you. Yeah.
Yeah, right. Yes. Right. And yeah, where was I? Right. And after determining this skeleton, we will greatly determine how we quantify the causal effects. So once we already fixed the skeleton, we can already base on it and answer what if questions. So here is the first scenario. We try to figure out a direct causal effect from the window area and to the heating load. To address this scenario one, we need to firstly set the treatment variables in DAGI and the outcome, which is the heating load. And then this skeleton will base on these relationships and the causal rules, such as Bechtel criteria, to examine whether they are biasing paths, which is in here, it's the red arrows. This biasing path means one needs to be blocked by controlling variables in the path to avoid this biased results. And interpretation is this causal skeleton try to get rid of the confounder between the window area and the volume, which is this part. And also it try to remove the false correlation between the external wall area and window area, which their confounder would be the wall-to-window ratio. So here's the suggestion generated from the causal skeleton. To correctly estimate the total causal effect from window area to the heating load, the wall-to-window ratio, ground floor area, number of floors, and height should not be controlled to eliminate the biasing path. That means if we want to have the direct effect from the window area to the heating load, we have to select buildings with the same volumes and with the same wall-to-window ratios, and the shape can be different. And from this perspective, from a perspective of the design process, this answer also deliver another layer of the information. We should only start considering the window area of the building when we have set the above mentioned features. Then is another scenario, how to estimate the direct causal effect from the building floor height to the heating load, which it's a corridor situation. It's an important reminder is that we should not infer or control these variables along this direct causal passes from the height to the heating load to create another bias path. For example, if I blocked here, we will create another bias path because this number of floors and height would be the causes for that. Blocking that would create false relationships between within each other and would affect results. And so the suggestions come as follows. If we try to correctly estimate the causal effect from height to the heating load, so the window area, external wall area, and volume should not be controlled to avoid this bias path. So as we can see from these two examples, the causal relationships identification process runs automatically, which is embedded in the process once the skeleton is fixed. The whole process, including the target identification for the treatment and outcome, and the conditions extracted based on the causal skeleton via this graph-based criteria, this whole process, what we call estimand identification. Right. So once we once we have the causal relationship and clarify them between the treatment and outcome, the investigation of this causal effect estimation is relatively intuitive. In this case, we set an experiment based on the last slide between the floor height and heating load, and we asked a quantification problem. What if I had changed floor height from 3 meters to 3.2 meters? What would happen on the heating load? To simulate this scenario, we set values to random features and keep another unknown to represent a certain stage of the ongoing design phase, as shown in this table. And here is the same skeleton from the previous slide based on the condition of the table. Say ground floor area is already set and extra. And the expectation of the height changes effects on the heating load can be written in the following formula. The distribution of the heating load given the condition of the height at 3.2 meters minus the distribution of the heating load given the condition of the height at 3 meters. And this formula also called a linear regression with the backdoor estimate, one of the simplest method to estimate conditional average treatment effect. And from the last slide, we already know that we should not involve this window. We should not condition on window area, external wall area, and volumes. So the rest of the features we should put condition on, and some already have the fixed value, and the rest we can feel free to sample from their ranges. So that would help us to get the correct results without this biased error. For the validation, we firstly run the first principle simulations by exhaustively generate 200 different runs of data sample within the range to get the ground truth result. The difference is the 218.52 kilowatt hours per year if we change the height from 3 meters to 3.2 meters. Then the causal linear estimation gives the results in the table with the conditional average treatment effect. The output shows that if the treatment variable's height increased from 3 to 3.2, based on the last slide's table's condition, it will cause an increase of the 207.28 kilowatt hours per year in the direct expected value of the outcome heating load. And for comparison, we also adopt a tree-based machine learning model, which performs the most accurate in heating load prediction task. But to answer this what if questions, it's kind of like in the wrong position, because we assume that the machine learning model doesn't have the domain knowledge to control these variables and still sampling data in all input features. And we also run these machine learning models 200 times within the range sampling, and it generates the outcome as in average 47 kilowatt hours per year, which is super biased result. Right, so here are some key takeaways. Yes, please.
Just a quick question. So you mentioned we shouldn't adjust the window area and some other factors. But did you find out we should control some like confounders for estimating the effect of the change floor height?
Well, in this, based on this causal diagram, causal skeleton, if we have our target of treatment is height and the outcome is heating load, if we click this two in the DAGT, there shows no red arrows, so there's no biasing passes, so there will be no confounders between these two. So in this case, we don't, but in the last slide's case, we do. last case we do, there's a lot of biasing passes here. So it's really, these skeletons encode these causal relationships, and based on this backdoor criteria, these separations and so on, it will gives you the conditions, which variables is conditional, which is not. So yeah.
Thanks. Yeah. Cool.
Yeah. Thanks. Right. So we already come to the end. So I just talk about some key takeaways. So first, in our domain, parametrics dependency check is important. And the second, in this paper, we do an analogy between the personal experience and physical knowledge, and to provide the channel for integrating the data-driven and knowledge-based method through the causal directed acyclic graphs DEX. This separation would also achieve a fast cross-sectional examination and avoid conducting the wrong conclusions if we just relies on machine learning models. And this causal model provides a data-driven knowledge extraction for design process, and it will reduce the computational difficulty. And this causal model allows user to quickly check potential design alternatives in a higher dimension. And then we clarify the boundary of the design assistance based on DEX, and the growth of DEX with reduced uncertainties aligns with the nature of design process. And finally, we propose a 4 steps framework, including 2 parts. One part is causal structure finding, and another part is causal relationship quantification or estimation. Yeah, so that would be my 2 pieces. Thank you.
Thank you, Xiaochen. Yeah, very great presentation.
Thank you.
Does anyone have any question? So maybe I can just follow up the comment that just made. So can you go back a little bit backward slides?
Which slides you mentioned?
The causal skeleton.
Okay.
So I think you show, I remember you showed 2, like one is for estimating the effect of building floor height to heating load. Another one is another one, the causal effect from window area to the heating load, right? So you are showing, and I think I remember you just demonstrating the first causal effect, the floor height, instead of the second one, the window area. But I feel like the second one is more important because you know, usually when architects design, you know, they try different variables. Usually they always control, like keep the other factors the same value, like the external wall area, and compare what's the effect of changing one variable. And for the second scenario, this one is, you know, we should control the confounder, right? And this one we should control, and instead of now adjusting. So I feel like this one is more important, but you didn't show like your calculation for this scenario. So I'm wondering what's the reason beyond that.
All right, we do consider this situation. The reason I choose for the building height to heating load this as a quantification case is that, as you can see, I used to say that this is more earlier design space because it's a kinship. You determine the geometry first, and then you know the window area based on wall window ratio and so on. So if the architect, you know, when he designs to a certain level and he got a customer request to say, okay, you have to change the floor height from 3 to 3.2, which he already detailing a lot and put a lot of parameters in there, and changing heights would affect way more different parameters than the window area. And that would be more interesting cases for us to demonstrate it, because in our, let's say, toy case, the window area would directly go to the heating load. There would be no further, there will be no design stage in between. So of course we can demonstrate the quantification results, but it would, to our perspective, it would be less interesting. So that's my thought. Yeah, because actually in here we said that what if I had done questions? So it's kind of the purpose. We try to have this way up.
Thank you.
Right. Thank you.
Perfect. Yeah.
Which are the next steps that you're planning to take on this research?
Oh, that's a big question. I can say because really, to be honest, the causal inference has a really it's a really big topic, and one direction, of course, we would go into more realistic examples, which would really benefit or really benefit the domain by adopting more sophisticated cases. Like example I mentioned before, maybe there would be causations between the indoor temperature, outdoor temperature, and building occupancy for the energy system dimensioning. So one direction would definitely be more depth in the domain. And the second, I would say, this causal inference is not only for this parametrics representations. It also goes for time series. It also goes for the graphs and so on. So that would be really wide open questions. And we would see the feedback from the community and see what we can do further. And to be honest, my personal plan is, because this causal inference is kind of the final, it's kind of the perfect knowledge embedded format. We can combine the knowledge into the data-driven method. So the further step would be we try to also combine another knowledge to see whether it can also represent in this way and embed it into the machine learning or data-driven method process.
How does this differ from another approach that is named physics-constrained machine learning, basically where you have an artificial neural network?
Yes, that's
then you give some physics constraint, like for example, gravity is pushing towards the bottom, or if you turn on the heater, the room can warm up, it cannot cool down, and things of that type. Because how the two models differ?
You mentioned the physical informed machine learning. Yeah, that's a really famous paper. Yeah, I read that paper. In that paper, they give the constraints on the either the machine learning rules or the objective functions to make the machine learning adopt more into domains and have more explainability. So that's actually right. That's one of our target to adopt it into our domain, but we put it into a broader scope. We actually have a 3-stage of embedding knowledge into the data-driven process. So the first stage is just really easy. We call it the data augmentation, which we have machine learning model, and this machine learning model can accept features, and we can use our first principle model to generate some data and put as extra input for machine learning that could reinforce some patterns for the model to learn. For example, the day-night patterns. If we put machine learning directly learn from historical time series data, it would be complicated. It would be really how to say, it would be really fuzzy in the bottom and in the top. But if we also simulate these patterns from the first principles model, really easy one, and inputs into the model, the accuracy will enhance. So that's the first layer. And the second layer, we try to do more like the physical informed machine learning way. We can manipulate these learning rules, objectives, functions, and also the machine learning model organizations to embed our domain knowledge into machine learning. Actually, me and Professor Geyer, we have another research called component-based machine learning, which we decompose the building parts into based on its components, and organize it as an output in the new building shapes and do the outputs, it would have certain extrapolation abilities. So this would be the second layer. We integrate our domain knowledge into the model itself. And the third would be the optimal one, which I start with this causal inference, because this causal inference gives the machine learning model or gives the computer the ability to learn causal inference directly from the data. So we don't have to, use our expert systems to hard coding every rules, like if, right? So this would be the third level, and this whole 3 levels would be our general objectives. Right.
I see that in one of the references that you have there, that is titled Explainable AI for Engineering Design, a unified approach of system engineering, component-based deep learning. One point is that this idea you're thinking not to apply only to buildings, but to basically any type of engineered system. Are you aware of any major efforts on trying to apply the causal diagram, particularly DAG, into the design of other type of engineering system? I'm thinking about integrated circuit or other type of engineering product.
Definitely, most definitely, because me and my professor, we have more domain knowledge into the building design process and building engineering, building energy systems. So of course, that would be our priority to adapt all this explainable AI with these causal models into this domain. But of course, the paper we have broader ambitious that can be adopted into the general engineering problem. So we try to extract the essence out of it. But if we land on the cases, we would apply our domain's cases.
And do you think that this type of approach is most useful to describe physical or chemical processes or human behaviors? Because my previous, I have some minor exposure on the topic, and all the examples that I see are usually from the epidemiological, criminology, psychology aspect, where it's much harder to give a causal relationship between things compared to the physical domain.
Yes, I should elaborate a little bit of our research backgrounds. Our research background is to develop a machine assistance to give the informative feedback to designer, more specifically regarding to energy performance, environmental impact, and costs. And these are 3 different objectives, and we have a set of these features might present in here. So if we want to sort it out, which is the most important for this objective, it would be really hard. So that's why we come up with this causal relationships, and also with this explainable AI to help us to, we can adopt more algorithm to, automate this process, and really gives a trade-off of the informative feedback for a designer. And to my experience, if we try to find the causal relationship from the user behavior, it won't be really hard to extract this causality from that, because in time series it would be the Ganger causality from it. So it would be equivalent, difficulty wise, equivalent to the physical one. I don't know if that answers questions.
Yeah. Thank you.
Right.
Yeah, just a follow up on that. So my thought on this is the main difference between Stefan mentioned what is I can understand what is the difference between machine learning method with physical constraints compared with your causal inference and plus some machine learning algorithm. So what's the main difference? I feel like if you just give some physical constraints to a machine learning model, it doesn't differentiate. It doesn't understand what's the structure there, what's the interaction between different physical variables. So you just give some constraints, but this causal inference can help illustrate the structure of among different physical variables, so that we can understand which variable we need to control when we want to achieve some specific objectives. So I think that's the big difference and the biggest benefit of using causal inference. Even we understand the physics between each data points, but this is just some single causation. But if we expand our scope to a larger system, like a more complex system, very difficult for human, even if we have the domain physics knowledge, it's still difficult to understand the system level behavior. That's kind of my understanding.
Yes, correctly. Yes. Thank you for notice. That's actually the very inner drive of us to introduce this causal model into our domain. And this is not my causal model. I just bring this concept to our domain. So yeah, right. And like you said, in here we have to think in a machine way, because machine doesn't understand what its floor height, what its floor number of floors. It just find causality directly from data. So this rules we can apply for any data we collected or we simulated, and find the hidden relationships we can further analyze. Or it would be, if a data set would be too complicated for us to all figure this out. In here, in the case, we have like 15 different parameters, and this is already really basic parameters. But imagine that if we try to manually generate this graph, it would be hard, and sometimes it would be also different from person. And I found that this algorithm and structural finding is quite accurate. I didn't mention that, as you can see, it also shows that these two variables is not correlated, or it's not have no causation to the heating load, because they are internal U value of wall and internal floor U values. This two won't affect the heating load. So yeah, that would be a really nice, computer assistance for us to structure this domain knowledge, store it, and try to accumulate it and put it into more complex systems that we can expand our personal horizons.
Super. Thank you very much for taking the time talking with us. It has been a pleasure.
Thank you.
Thank you.
Thanks, everybody. I'll just stop recording.